everyone, welcome to the Houston Museum of Natural Science. We're just about ready to get started. We're here live from the Houston Museum of Natural Science sundial. And I'm here, we're gonna get started in just a couple minutes. We're gonna let a little bit of time here for some people to join us. As you can tell, the sundial is under some construction. It's having its travertine cleaned up. And we will be starting our broadcast here real soon.
Hi, Pat. It is 1 o'clock. And the sun, I can show a video of what it looked like last week with the sun on it at some point if you'd like to see it.
Okay, well, first let me just go ahead and say what's happening here at the sundial.
Okay.
And then we'll turn it over to you when I'm coming back downstairs. How's that?
Sounds great.
All right. Well, so let's go ahead and get started. So I'm Pat Rife, professor of physics and astronomy at Rice University. And I'm here at the Houston Museum of Natural Science. I'm here in my Houston Astros astronomical t-shirt because the Astros have been doing an astronomical job.
The best record in the American League.
The best record in the American League as of last night.
They won 7 in a row, and they are now the best record in the American League.
And the best record of the American League. Okay, so I am here joined by the planetarium astronomer, James Wooten. So here's James. He's an expert on all things astronomical and all things Astros. So James, give us a brief overview of the sundial here and what we would see if we had a sunny day.
We like to have activities on the sundial every equinox and solstice because that gnomon you're seeing there has a ball of the type of holes in it. At the equinoxes and solstices, the sun will shine through those holes and cast an image onto the sundial. With a sheet of paper.
Yeah.
Pat, we seem to have lost your connection.
Focus the image of the sun. Sun shadow. Sorry, as the shadow of the gnomon. 1 more hour has passed during the day. Unfortunately, there are 2 reasons why we can't do activities on the sundial for this solstice. That's because the one thing, they're fixing up in August. We'll be back on the sundial. We have some activities scheduled with our interns for August 6th, which is on average the highest day of the year in Houston. Yeah, Houston, we have 2 seasons.
Except for and that's what it's case. And we'll talk a little bit more about our August broadcast.
So we have the work and the clouds appear. Therefore, instead of seeing a gnomon shadow, we're all in one big shadow of that giant cloud. So we can't do activities we would normally plan for the sundial. So instead, we have Dr. Carolyn Summers downstairs who will show us some of the activities we would be doing if we had the sun. So
that's right.
Stay tuned in August. We'll be back out here in the blazing heat, and we'll show you more what the sundial can actually do.
All right, thank you, Mr. Wooten.
I am, and we will go silent and take you back to Carolyn. And Colin, why don't you spotlight Carolyn? And
all right, I want to welcome you to directly below the planetarium. And I went out last week having read the weather reports and decided I better have a video to show you how the sundial works. And it really is quite cool. And we don't want to lose our precedent of trying to do, okay, let me share something every sundial. So I want to show you how the construction works. So here comes our first, we're going to optimize And I'm not going to, well, maybe share sound. I'll share sound. Okay. Hold on. There. Now, this is what the sundial looks like on a sunny day. Colin, everybody, are you seeing this okay?
Yep.
All
Yeah.
right. Okay. Now, windy sunny day. What they're doing is removing the travertine. And there's the planetarium behind. Now, this was done at noon. There's the telescope at the top of our sundial. And at 12 o'clock local time, you can see the sun. Now we're photographing it here. All right. So
focus point is right there.
So let's go down. I'm going to pause it. The light goes through 3 different holes, one for the summer solstice, one for our equinoxes, and one for the winter solstice. And the light from the sun, which I just showed, back up a second to the sun. And I'm going to turn down the sound quite a bit. And the light goes from the sun. It was a cloudy day even then, but okay. Through here and down, and he's holding right here a piece of paper in just the right place. Now, it's not as good. This was done on last Thursday. So it's not quite as good as it's going to be today if it were clear today. But at this elevation, he's photographed it. And then we actually shot a picture of it. And there you can see, that's an actual, now this is soft here because this is not in focus, it's just a mask, but you can see that the edge of the sun is sharp. So we're getting a real image of the photosphere of the sun. And this happens, and normally when we're not trying to clean up all our travertine and make it look nice and tidy again, which is what we're doing now, normally this is a fun thing to do. Bring a piece of paper with you or improvise. And then you can, on the days close to the solstices and the equinoxes, you can do this same activity, but you have to be also close to local noon. And local noon in Houston is not 12 o'clock. We keep Central Daylight Time. It's 1 o'clock, except we don't live on the time zone meridian either, which goes through Memphis and New Orleans. So what you have to do is add, on average, 22 minutes. So at 1:22, plus or minus, and we'll show that in a minute, you will see this effect. And it happens, for about 10 to 15 minutes before and after. But it's a very cool thing. It's always open, except when we're trying to renovate it. And that's what it looks like. And there I am holding it. And you can see the light goes through the telescope up there. And it comes down, and we have an image of the sun. And it really is quite fun to do. Now, that image at local noon is on the north-south line. This brown line on our sundial runs north and south. This line here, the black one, is for telling time. Our gnomon is adjusted to take care of that pesky 22 minutes, which effectively is the distance between here and here on the motion of the sun, so that we do your clocks, even though you have to go with standard time and not daylight savings time, otherwise the clock works. Now these dots here are adjustments you also have to make because the sun is not a perfect clock. It does run a little fast sometimes and a little slow sometimes. and you have to make these adjustments. It's called an analemma. Pat may want to talk more about that in just a minute. Now, that you can see it wasn't in focus because it's on the flat part below, but you can see where the shadow is. That's average time. That's standard time is here. Actual sun time is here. And notice all of these Roman numerals, that's 10 o'clock, 11 o'clock, 12 o'clock, 1 o'clock, 2 o'clock, 3 o'clock. These lines etched in black on our sundial tell time. And every sundial will do this. In fact, if you want to make a flagpole in your front yard into a sundial, then just go out one day and use your watch, use your clock, use your iPhone to mark the right times, and it'll come back later and it'll work pretty well all year long. Now, I want you to look here very carefully. See the line? Can you see it with my pointer? My foot is pointing toward it. See how that circle is not quite on that line yet, but it's close. That is the line for today. If we went out this morning, the sun would be a little bit higher than it was last Thursday and a little bit closer to the middle of that line there. That is the shadow where the gnomon shadow hits at June 21st, 20th, 21st, whenever the solstice hits. This is for May. And we have lines like this all over the sundial for every month of the year. Okay, now what I'm going to do is look at from the outside coming in. There's a line for December, November. And notice the analemma dots. Half of them, by the way, have been replaced. They're fixing them. And that's your correction points all the way down to construction included, back to where we started. So that is June 21st, May 21st, or July 21st, April 21st, or August 21st. This line is kind of cool here. That is March 21st or September 21st, and it's a straight line running due north to due south. And that's for the equinoxes. And then if you keep going, I don't know if I can do this or not. Let's see. That's for February or November. No, October or February, excuse me. January or November, and that's December. And that is our fountain, which is being cleaned out as well. So our sundial not only tells the time of day, it also tells the time of year and gives you corrections. And once again, the brown line is due north. The other lines work with your clock to tell you the time it is.
You want to pause for a second? Let me explain the...
Okay, let me go through it and I'll back up and pause for Pat. But that's what we're doing now with our sundial. Now, hold on, Pat. What part would you like?
Well, let's go back and look at the analemma.
Okay. Okay, I'm going to start here and the analemma will show up, okay?
Okay, so pause here for 1 second.
Okay.
As Carolyn points out, what her foot is right now is 12 o'clock Central Standard Time. What the shadow is solar time. Because it's daylight saving, as you pointed out, that gray line is on average 1 p.m. Central Daylight Time. But the sun is sometimes a little...
Pat, can I stop you for a second? You've got no audio. We're only hearing you through Carolyn's computer.
All right, is that...
Yeah, there you go. That's, yep.
And I'll mute me.
I'm so sorry. Yeah, it's bad to have more than one mic open in a room. Okay, so her foot is at 12 o'clock Central Standard Time. But because of daylight savings, it's actually more like 1 o'clock Central Daylight Time. Okay, whereas the brown line, as she pointed out, is solar noon. Now, on average, the solar clocks are a little bit ahead or a little bit behind a true clock. And even the Romans knew that when they were using sand clocks, they noticed that the time from your sand clock could be a little different from the time of a sundial. And that difference is consistent. It's always late, early in the year, and early, late in the year. So those little silver buttons show the time of actual 1 p.m. Central Daylight for the time through the year. And you notice those dots are really close to her foot in June and July. So the correction is not very much. But if you move ahead on the video until we look at where the dots are in October and February, you'll notice that the October and February dots are really far. And that correction can be 15, 18 to 18 degrees. Okay, so pause right there. All right, so see those silver dots on the right side? There you go, the ones that haven't been reminds. And so the question is that February or is that November? And what I just said is the sun is late in the year. So those are October, November dots. Whereas the sun is early in the year. So the dots that are missing that are on the left are the February ones. Okay. And together it makes that figure 8, which we call the analemma. And in the old style globes, you could see it in the Pacific Ocean, where the vertical would be the declination of the sun. So when the sun was at high northern latitudes, that would be the top of the and when it was at southern latitudes, then that would be the bottom of the animal. And we have a diagram I can show you from our website. Okay, so I'm going to turn it back to you, Carolyn, but I can show our website with these diagrams when you're ready.
Okay. Now I'm going to Yes, Pat and I have to mute and unmute. Stop sharing, and I'm back. And okay. All right. Woo. Now, what we also do when we go outside on these sunny days we don't have is that we try to do fun things with the sun. And also we try to teach some astronomy. So I think I'm going to teach the astronomy first and do the fun things second, if that sounds okay. Because I did the sundial on Thursday of last week. And then Friday we went outside and we cooked and burned and did all kind of fun stuff. But let me do this first, because this really will explain why it happens. So hang on. I have to go to here. And I'm not going to share sound on this one, so I can talk over it. Now, the question is, I have to find this on my screen. I see it. I have 5 videos open. Okay. Now, everybody see the Earth. Okay. The Earth rotates. Because it rotates, the sun seems to move across the sky from east to west. So I'm going to pause it. Those lines you saw, the black lines on the sundial marking every hour, are needed to mark the hours of time during a day. The sun is not doing this. The earth is. So basically, the sun is in the same place for one day. And what we're doing is we're turning under it. So sunrise happens when you're right here on the earth. You're moving eastward. The earth turns eastward. So sun rises right here. You look eastward and the sun rises right in front of you. Then you wait about 6 hours and you're right here. Then the sun is as high as it can be in the sky. Now, how high it is depends upon the tilt of the earth. If we tilt more away from the sun will be lower. If we tilt, this is our tilt line here. If we tilt more toward the sun will be higher. So that should make sense. And then we wait and we travel around to the back side of the globe, and then we're having sunset. We are moving eastward. We look behind us, behind the motion, the direction we're moving, and we see the sun setting in the west. And then we have the stars moving at night. So day and night, and the motion of the sky is not the motion of the sky. It's you looking through the window of the atmosphere as you live on a turning spaceship. So it's your first indication you're an astronaut traveling through space. You're spinning. Now, I was going to show, here is the morning sky. The sun rises in the east. There you see it. The planets rise ahead of the sun, by the way. When the sun is on that brown line on the sundial, it's right there. So it could be higher, up to 93.5 degrees in Houston, and it could be lower, subtract the 23.5 from, it can go down to 37.5 degrees in winter. So the sun's height at noon along this south line, north-south line, is your measurement of what's causing the seasons. The sun is low in winter and high in summer. And then it sets in the west. Now, here is what our sundial does when it's clean and nice, and we don't have the fountain on because we're photographing it in a way we'd be sopping wet. So we turn the fountain off to photograph this. This is a time lapse. You'll see cars pull up here, buses pull up. This is morning, and we're going to watch the sun move, the shadow move, the gnomon making all this happen, and people running around. The museum is this direction over here on the right. So here we go. Buses pull up, kids get off. This was before COVID. Notice as the sun moves across the sky, the shadow not only moves in the opposite direction, caused by the rotation of the earth under the sun, but also the shadow gets shorter. It is shortest when the sun is highest, and right there is local noon. Now on your watch, it said noon when the sun was right here, but that's approximately 12:22 or 1:22, depending on whether or not you're keeping daylight savings time. And then we go into the afternoon. And the school buses come back and pick up the kids, and everything gets quiet at the museum once again. So that is how a sundial works on a daily basis. And it's because not of the sun moving up from left to right or east to west, because you're turning eastward under the sun. And it's very cool to think about that. As you watch all this happening, you're not seeing the sun moving, you're seeing your own earth turning. And it is a chance to really see it by watching the motion of the shadow. Now I had the moon in this image too. I'm going to skip the moon because we got plenty. So we're skipping the moon. Bye-bye moon. And we're back to right there. Okay, the earth goes around the sun once a year, and that causes the seasons. So here is a summer day. Notice the path of the sun, hour by hour across the day. When it's due south, it's the highest it can be. So then you've gotten used to this path. That's a summer path, and the trees and everything look just lovely. Okay, what does a winter path look like? Well,
notice it sets the east, north of west and rises north of south.
Okay, I've paused my video for the comments of the one next to me. And here we go again. Now the sun is rising south of east, and it's not getting nearly as high. And it hides among the trees a lot of the time if you have tall trees and you're close to them. And you might get snow on the ground if you're perhaps a little farther north than we are. Well, that was a dramatic difference. And that's caused by the tilt of the earth. Here's a graph, hour by hour, 14 dots. That's where the sun is every hour of the day in summer. Today, if it was just clear, well, the sun's still there, we just can't see it. So for in Houston, we have a 14-hour day on the summer solstice. If you live farther north, your day is even longer. Now let's contrast that to winter. Computer is calculating in case you're curious. And there comes winter. Now, that is really impressive. But if you think about it, you don't notice it. You don't perhaps know much about it because we live in a city, and in a city, so much is just lit artificially. We just kind of go about our lives, and we don't realize how dramatically different the height of the sun is. And it's something hard to teach in school because the kids don't observe it. Now, let's add the earth going around the sun, but I have included the tilt. See my tilt? The tilt is the same all year long, but we're on one side of the sun and then the other. So let's enlarge this image and this image. Making them bigger now. Stay tuned. Well, I promise they will. There we go. Summer, winter. Look at the difference. All right, same, exactly, except the sun comes from this way. The northern hemisphere is tilted toward the sun. And that's summer, and that makes the high path of summer. Winter, the northern hemisphere is tilted away from the sun. The North Pole gets no sunshine. And we have the low path of winter. And the southern hemisphere is getting summer. And over here, when we're getting summer, the southern hemisphere is getting winter. So this is one of the hardest concepts to understand, the one most often missed by everybody, including graduating seniors from Harvard. So it's something, it's one image to remember. And then when you come to our sundial, we will show it to you. And that perhaps makes it even more exciting. So just a minute. But it's a cool thought that the tilt stays the same. The North Star always points to Polaris. But now here's our sundial. Now we're going to look at the low winter sun, but notice the line. See, I told you, the line that goes straight north and south, that from the straight east and west, like there, that is the March or September. So that's September, August, July, June. That's the one for now. This was made in October, late October. And let's draw our sun. And the sun casts a long shadow. Why? You use the shadow length at noon. Because the sun is lower, the shadow is longer. Now let's compare that to the high sun of summer. Well, here we go. There we go. Now look, where's the shadow? Look how dramatically different the shadow is. Something else we don't notice, but it's impressive. The shadow is so much shorter. Now that was made, that's June, that's May. That was made about at the beginning of June, this picture. So now we can put them together on one picture just to see how this works. And that's how the sundial shows you not only the time of day, but also the time of year. So there. And I'm located, by the way, Pat and I both are. We're right down in here, below ground, below the Burke-Baker Planetarium, on a day that doesn't look like this one. Okay, I'm going to stop sharing.
Take over for a second.
Sure.
Okay, so that was a really good description. And one thing you might notice is some of her images looked a little bit curved. Those were designed to go on a planetarium dome. So a lot of how Carolyn teaches this is in a dome. And there's nothing that beats learning in a dome when it's a three-dimensional topic. So if you haven't come to the Houston Museum of Natural Science, come and see these in person. And if you don't live in Houston, then try your local planetarium. And we also have portable planetarium that will go anywhere in the world if you pay for us to come. Okay, but I did want to show you our website. So let me share this. Okay, sorry, my ears are hearing what you hear, so it's like 3 seconds delayed, and it's driving me nuts.
That's why I took mine off.
That's a good idea. All right, so here's our Sundial website. If you haven't seen it before, it's space.rice.edu/sundial. And so we post here anytime we have Sundial events, like we're doing hello today. But we also have a calendar that you can go to for information on events that Carolyn and I do free over Zoom. As she mentioned, we do it every equinox and solstice. And this year, we're also going to do the Dog Day of Summer to kind of celebrate the reopening. And I put in my information it was 22 years ago. I'm wrong. It was 32 years ago when we put the sundial together. So this sundial has that she and I both helped design, and the museum, of course, paid for, thanks to Ernie Cockrell. Put this wonderful sundial together, and it's been working for 32 years. So there's a lot of information about the sundial here on a PDF. You can download, if you're in Houston, a scale model of the Cockrell sundial and put it together. And we do that with children all the time. And then here's a website on how to use the HMNS sundial that James put together. So here's some information. Here's that time lapse that she showed you in a fisheye format or in a flat format. So those are there. And here is our calendar. And if you go to space.rice.edu, you'll see all of these things along the edge. And one of the things that's going to be coming up is 2 eclipses crossing Texas right away, one in 2023 and one in 2024, which is immediately as far as astronomical things go. So we'll be doing a lot more trainings on how to safely observe the eclipse. So anyway, here's this summer solstice live stream, and as we have more activities, we'll be posting them. So that's where you get to the calendar. And if you're not signed up for one of our mailing list, we have different mailing lists in the bottom that to sign up for. We also do it through Meetup, and so I know many of you have joined us through Meetup, and that is a lot of fun. Okay, so then going back to the sundial information PDF. So here is a little information about it. Here's what I looked like 30 years ago. and here's that analemma with now all the dots together. So you can see the fact that the true sun is late in the year, and early in the year. And the true solar noon is exactly when the shadow goes exactly to the north, because the sun will be exactly in the west. So, and here are these alignments that she was telling you about. The spring and fall holes through the ball. So there's some images here of the sundial that you can get to from our website. But all of these things you can get to from space.rice.edu, which is a great way to start. And we've got a lot of resources available. And we do a lot of streaming of talks and planetarium shows, and we'd love to have you join us. Okay, now I'm going to throw it back to Carolyn, and it says you're not seeing what I'm talking about. Am I not sharing the screen?
You're sharing the screen.
Okay. All right. So I'm going to now put it back to Carolyn, and she's going to show you some of the fun things you can do on a sunny day. And so I'm going to let her go back, and I'm going to mute, and you're going to unmute.
Okay, I'm unmuted. Now, we went out cooking. This takes this is a little story. In fact, I even have the stuff we cooked. I think I need to show you the cooking video first, and then we'll even look at the food that we cooked, which unfortunately we cooked on Friday, so it's kind of that way. But anyway, so let me see. All of the stuff that I'm going to show you is something you can do, and since we want the best chance of this stuff actually cooking, we're going to have our hottest day of the year. Hopefully we believe the sundial be up again, so we can show the sundial and we can show cooking as fast as we can possibly cook it. It's pretty hot last Thursday. That's Friday. That's when we did our cooking. So let me go back to screen sharing, and let's see. There we go. And I think I'm going to keep the sound because I was narrating it, and we may decide to turn it down afterward. So let's see how this works. All right. Now I have to find, that's not the one. There we go. I have to clean my screen up a little bit here. Now here I am outside I decided to cook with my interns on the roof of the museum. It's a private roof, because then I could have all this happen and not have to guard it so carefully. Now in this picture, you'll see a whole bunch of different cooking. My hands are kind of on one of the cookers, and what's inside it, we'll find out. And then there's our sun spotter. Pat may want to talk about it later. This shows it working, producing an image of the sun. Another cooker, and then there's some more things. So let's see what kind of trouble we got ourselves into up on the roof. Okay, this is a solar cooking activity. Here you can see a pot with sunlight being concentrated on it. The pot has a top that's clear, so the sunlight goes in. Also, the black metal gets hot. We're cooking 6 cupcakes, but they're different colors, and they have and then 2 of them have light colored icing on them, just like you see here. We have put half the water you normally put in, and you can see even that water is appearing on the top. Now, if we look back behind, we have used cones, which are much simpler. We've aimed them at the sun. You can see the sun is concentrated in them. We have brownies, cupcakes with light vanilla frosting, and chocolate. Huh? So these cook once again less. Hold on. Say it. Sound louder?
Yeah. No, it's not. No sound at all from the video.
Okay, let's see how this works.
Hotter than before as we leave them.
Do you hear it? No. Okay, I will narrate.
We are hearing it on the Zoom, yes.
Okay, all right. So I want to, is it too loud, Colin, or is it about the right height?
No, it needs to be a little louder.
A little louder, okay. We'll try this. Tell me if it needs to be even louder.
And compare them.
That's pretty good.
This is a concentrating cylinder.
A little louder,
and
maybe.
All the light from the sun is being gathered and focused in there, and the heat is being held. And we're cooking now little baby sliders. And we're going to see what happens to them. Now you can see they're just starting. They're not cooked at all. So in they go. and we'll seal them up and check on them after a while. Using solar cells to collect energy. We have a fan turning back here. Now you can discover things from this. If you hold it like this with the sunlight shining on it, it turns real well. If you hold it like this, like that, it doesn't turn at all. And so one important thing is to watch the tilt. And this kind of magic moment, the tilt is such that the thing begins to turn. Our fan begins to turn. We can watch it this way. It turns nicely because it's almost aimed right at the sun. But if I turn it, now look at it, see it's getting slower and slower and slower. And at that angle, almost vertical, it will hardly turn even in bright sunlight. And then finally, of course, the sun doesn't get to it at all. So exactly how you angle a solar cell really determines how much sunlight you get from it. This particular material will cut out as much sunlight as we lose by going to Mars. So 40% of the light. So there's our, we don't hit the fan, there's our fan turning. If we take this off, it turns much faster, illustrating that we do have a problem on Mars in that when you lose part of the sunlight, it's like tilting it kind of. When you lose part of the sunlight, it cuts out much more quickly because there's less sunlight hitting it. So going to, with the cookers, have to do the same thing. Once we get these cookers cooking and we see how well they cook in Earth light, we have to see if we can make a cooker that will cook as well if you cover it like this, because now the cooker is only getting the light that it would get on Mars. So will this cooker cook on Mars? That's one of the experiments we're doing this summer. We're going to first use the purple one. Okay.
I'm going to pause right now. We are going to show how you can use, now I kind of went over the board here. You don't have to use the Fresnel lens that big. This just guarantees it's going to really catch on fire. But you can focus sunlight. And in this case, we're going to focus it on popsicle sticks. And we could actually etch our names in popsicle sticks by burning the popsicle stick using the sunlight. But let's see what happens.
Concentrate the light. It just at the focal length. And look at that. Look how fast. I could put names on this. We could do almost anything on this thing. All righty. Now, let's try the blue one. Notice it doesn't catch on fire quite as fast. Hold on. There. But it's pretty effective, and if I concentrate at exactly the same point the whole time, I might actually set it on fire. Let's find out. Well, that was impressive. Now the yellow one. Be careful not to set your clothes and shoes on fire while you're playing. Okay, you ready? And we can see that it's not burning quite as well because the yellow reflects more light.
I got to pause here. This is why you don't stare at the sun, because you don't want to concentrate the sunlight on your retina. Given your eyes aren't that big, still, the sun can make damage.
But it's still doing a pretty fair job. Wow. All righty. Are you ready? Are you sure you're far enough away?
Oh my God!
Orange one. Now blow up another one while you're over there. Takes much longer. Go take it down a little bit. Hold on. Okay, the yellow one. Now, this blue would normally pop pretty fast, but we're going to try to just Much.
Now we're using just a really small Fresnel lens that you get as a magnifying glass, like like Office Depot. I didn't use the little ones you see, but I'm using the bigger one. Watch.
So we did it with just this. Let's see if we can do the pink one with just this. I'm not even trying to make the little one work. I'm not going to use the bigger one.
Now, when you watch the pink one, notice the problem is it's so big that the wind is getting it, and I can't hold the light still. Now, the pink is almost a white color. It's not going to absorb as much heat as the darker ones, but more than that, I can't keep it still enough to concentrate all of the heat in one place.
Get a little hot. I'm not sure we'll get hot enough. No, we'll have to use the bigger one. So,
now it becomes a matter of sheer determination that we're going to have the sun pop this balloon.
this illustrates that the heat has to concentrate. It's a light colored balloon. It has to concentrate at the same place. Once again, it's a light colored balloon, and it's okay. Another volunteer, come over here. Bring your tongs. Well, you all are so easy.
This is after an hour of cooking, probably a little longer than we needed to.
And look at that. I think we probably left them in too long. They certainly cooked in sunlight. Those are the sliders. The very, very well cooked. There you can tell in that one especially. That's definitely nice and sizzly. The very well cooked sliders. This oven will get, because it's sealed and concentrating sunlight, it will get up to 300 degrees. Okay, and we can look inside here. What's interesting is that our cooked cakes have definitely cooked. Our brownies look cooked. The icing on one of them is run off. The icing hasn't done as well like you do in a regular oven. Probably put the icing on last after you finish the cooking. But we definitely cooked our brownies and our chocolate cake and our spice cake. And this is the simplest of the ovens. But if we look inside this one, especially if you look inside close up, we've actually burned our cake, and that definitely is cooked. It's loose inside there. If we look in here, I'm going to touch it. It's very solid. It's definitely cooked. And here, well, our brownies are a little gooey, but that's kind of the way brownies are. So, a little bit gooey for the brownies.
Uh-oh. Okay.
That was really exciting, Carolyn, and I think one thing you have to be aware of is that if you've got a clear plastic water bottle left in your car, people have actually scorched their seats in their car when the sunlight came through the window, focused through your water bottle, and focused on the seats, and people have actually burned their seats.
Okay, here you can see the cookie. And so if you want, Pat will have to post it for me. We can post this pattern, and you just make it out of aluminum foil or something a little bit shinier, and it will concentrate all the light down in the center. In fact, I don't have a light, you can see it concentrating it, but anyway, and just put your food in a cupcake holder in the middle, and it will cook it. Now, waiting 30 minutes for a brownie is a little hard, but it does demonstrate that solar cooking works, and that's the different cookers there. Oh, here's the one that burned. Brownie didn't burn. It had a little more water in it. That's the cake. It's hard as a rock. I will keep this as a demonstration item from now on. The color mattered less. Well, actually, here's the third one. It got a little bit where there was a raisin, it got kind of burned, and it's very hard, so it cooked too long. But the lighter colors are a little harder to cook than the dark ones because the lighter colors reflect more sunlight and absorb less. Pat has the they kind of stuck in it. Oops. Oh well. And they still smell like sliders. Like that. The bread kind of cooked too much. I would have done it without the bread and put the bread on later, maybe. You have to play with the recipe, and everybody in here will agree it still smells like cooked food. So it does work. And then Pat has the oven behind her. The reason we're going to try to cook in August is see if we can actually cook with the filters on like you cook from Mars. Okay, Pat, I'm through with my videos and my foolishness. I hope people will come to the museum and in March, I think not March, August the 6th, we'll probably cook early in the morning. We're not crazy, and see how well we can cook 11 o'clock-ish or so. See, maybe 11 to 12. An hour will cook almost anything if you have a concentrating where you're putting more sunlight in it than would normally be collected if you just set the thing out. Okay.
And the cool thing about our sun is it's coming back. We're starting to get sunspots again. We're starting to get some solar activity again. So this might be a good time if you're thinking about going to a northern climate, Alaska in the fall. You don't want to look for the auroras in Alaska in July because there's no dark. It's hard to see the aurora if the sun is shining on you. But statistically, the best time to see the auroras are the spring and fall. And now that the sun is coming back, it's getting more sunspots and more solar activity. We'll be able to now see more sunspots through the sundial. And speaking of sunspots, another cool way to see sunspots is to use what's called a sunspotter. Now, this is a commercial product, and it's not super duper cheap. But it is a great way to cast an image of the sun onto a piece of paper, and so it makes an image that's about this big around. So if there are sunspots, you can see them and you can sketch them. So this is a good thing that we will bring out whenever we do solar activities, solar days.
Yeah, they saw one in my video.
The other thing, as Carolyn mentioned, is anytime you want to do solar observing, you be sure to use special filtered glasses. You can get them from a number of stores. I like Rainbow Symphony. They have ones that are made out of paper and some that are made out of plastic and some that are actually little binoculars. I like to go with a reputable dealer because last 2017 for the eclipse, it turned out there was some fake eclipse glasses that were not safe, and so that's something we really want to stress, that anytime you look at the sun, you use projection techniques or you use special solar filters on your glasses or binoculars, and if you have a solar filter on your binocular, you put it on the big fat end of your binoculars, not on the eyepiece end, because you will burn a hole through your filter if you put it on the eyepiece. As Carolyn showed you, when you focus the sun, it's even hotter than if you just look at it directly. So Be very, very careful. Never look at the sun through a pair of binoculars or any telescope unless it's got a filter at the fat end, not at the eyepiece end. And we'll be doing a lot more trainings on safe solar observing as we're getting closer to the 2 Texas eclipses that are coming in October 2023 and April of 2024. We have a new website, space.rice.edu eclipses, where we talk about these eclipses coming up and where to go. And if you are thinking about taking a trip for April 2024, it's not too soon to be looking for locations, because they're going to fill up fast, and it's going to be more and more expensive to get a place to stay the longer you wait. But Texas and Mexico are going to be the best, statistically the best weather to see the April 2024 eclipse, and probably also for the October one as well. The October one will be an annular, not a tolar. And again, we're going to be doing a lot more trainings on eclipses coming up. So if you're not on one of those email lists, be sure you sign up so that you get the information on our upcoming trainings. These are sponsored by Rice, by NASA, and by the Houston Museum of Natural Science. And so we're happy to be able to provide all this for you for free. Now, you need to buy your own equipment. I can't do that. But we do want to make sure that you can see these wonderful eclipses coming up very, very safely.
And in the meantime, if you come to the museum on a sunny day, the sun will perform. It may not make a circle on the sundial, and you can't get to the sundial till August, but it's there. You can see it. You can enjoy all of our other exhibits, and we do have a whole hall of energy. And just, we'd love to have you. And some new planetarium shows. We have one called Are We Really Alone? That's become very popular and really addresses those UFO stories you've been hearing about recently. So,
okay, we have a little time for some questions. If anybody's got any questions, you can put it in the chat. You can raise your hand and at that bottom edge under reactions, there's one that says raise hand. If you raise your hand, I'll call on you and you can unmute yourself and you can ask us questions. We are here for you. And we want to make sure anybody has any questions, we be sure to answer them. If you want to open your video and let us take a group photo, we always enjoy taking group photos. Any questions?
we told the whole story, Pat.
Okay, well, thanks everybody for joining us. And as we said, there'll be for our August one, we'll put on the calendar, and we'll send out the notices to all of those mailing lists. So put yourself on one of them. What will we be presenting in August? That's a good question. Well, hopefully
we'll cook it.
We'll talk a little bit more about some of these same things, about the seasons and the tilt of the sky. And the question is, how come it's hotter in August than in June? Now, she just told you that the longest days and the highest in the sky sun is today. So how come it's hotter in August than it is in June?
Especially in Houston. And what we're going to do in August as well for our event, you must tune in. We're going to prove we can cook on Mars with sunshine or not. So that's why we picked the hottest day of the year in Houston. And we're going to add our solar shields to all our cookers, and we're going to see if they'll cook and see if we can invent some new cookers that concentrate better to make use of the fact that we're going to lose 40% of our light when we go to Mars. And when you think about Mars, after all, where are you going to get energy? You're not going to get fossil fuels. So we better figure our sunshine out. And so we're going to add that to the list of cool things we're doing. We're also making some neat videos with our interns. We may show some of those too, about the Earth and Mars.
And Carolyn, you have a new planetarium show that just opened, right?
Yes, as I mentioned, Are We Really Alone? With all of this Pentagon releasing of all of the interesting, crazy things the Pentagon is releasing, there's the question of Are the aliens here? Could they be here? What are the UFOs? Oh, they're not UFOs anymore. They're unidentified aerial phenomena, the UAPs, but it doesn't matter. It's the same problem. And we kind of go over all of that in a very objective kind of way and talk about how to analyze what may and may not be. And that's kind of the question we promised to answer, and we answer it. We even built a warp ship for this, and we'll explain why in the show.
Okay, we have a question in the chat from Doug Wilson, and he says, is the reason for the sun time running fast or slow due to the elliptical orbit of the Earth? Yes, but that's actually the smaller effect. There's two effects that make that change. One is the elliptical part of the orbit, and that's what makes the analemma asymmetric, okay? But the main reason that you have an analemma is the tilt again. So if you look at the latitude of the sun as a function of time, it makes a sine wave, okay? It goes from south where it's almost standing still, so it's solstice, is the winter solstice, which means standing still, and then it goes through the equinox, and then it stands still in the north at the summer equinox and comes back through. But the sun is moving along that sine wave in a uniform way. So think about it. It's moving along that sine wave in a uniform way. But when it's going like this, we measure time as if it was going straight across. Okay? We're measuring time along our equator. We're assuming by our clocks that that sun's path is at equal speed along the equator. But instead, it's going faster here, slower here, faster here, slower here. And so it catches, on average, it's traveling along the equator, but in certain months of the year, it's going a little faster along the equator or going a little slower along the equator, and those things accumulate, and that's why the sun is...
There are 4 days when the equation time is 0.
Also,
Talk louder,
There are
talk
4
louder.
days when the equation time is 0. I'm trying to do it from memory. One of them is around tax day.
Yeah, April 15th.
One of them is September the 1st.
Yep,
Then you have Christmas.
Christmas.
And then in June, I forget which
It's
day.
almost the 4th of July. It's not quite the 4th.
Right.
It's just about the 4th of July. So it's April 15th, the 4th of July, Christmas, and
September 1st.
September 1st. So those are the days that it's almost exactly on time.
And the next days for the equation time are Halloween and Valentine's Day.
And there's actually a poem to help you remember that,
Yes.
which I've forgotten now the poem. But
Yes.
the way I just remember it, it's the sun is early, late in the year, and late, early.
early in the year.
That helps you figure out which way that it's going. All right. well,
Also, one more thing.
Yes.
We are closest to the sun in January. So even though the distance Mars to the sun versus Earth to the sun does affect how much sunlight you get at the planet Mars, the difference between where we are in January and where we are in June does not make our seasons. We are closer to the sun in January and we're not warmer. So for us, it's the tilt, not the distance, that makes our seasons. Okay.
All right. Well, listen, everybody, thank you so much for joining us. And we'll hope to see you again next time for the Pat Carolyn Show.
We're cooking. We're cooking next time.
We'll be cooking. Hopefully, we'll be cooking next time.
Bye-bye.
Bye.